All right. So, what did we say about this stuff yesterday, right? Let's kind of review where we were. We defined something new called a limit, right? And let's remind ourselves what a limit means. What is a limit? Yes, ma'am.
It goes near it, but not to it.
Okay. So we could kind of think of this, we could illustrate this with our calculus ant, right? The calculus ant, remember our highly evolved calculus ant that, well, two-dimensional, point-like in size, crawls along the functions. The limit of a function is what in terms of the ant? Okay, yeah, where it anticipates stepping when it gets to a certain x value, right? Where it actually ends up is completely irrelevant. Doesn't matter as far as the limit is concerned, right? The limit is just where the ant, up until it makes that final step, where does it anticipate landing, right? The other part of this that we need to add is that the ant, either the same ant or two ants approaching from opposite directions along the function, would also need to anticipate stepping on the same place for that limit to be meaningful, right? So if the ant approaching from the left thinks he's going to land one place, and the ant approaching from the right thinks he's going to land in a different place, that doesn't work, right? And that's not a good limit. Okay? That, in fact, it's not a limit. That limit would not exist. Okay? We looked at a couple examples. We looked at an example with a really simple function, a line. And remember what our strategy is, because this is important. We wanted to find out what the limit was as x approached positive 1. How did we get our answer? By plugging 1 into the equation, right? Because this function is just a simple line. So isn't the easiest way, and this sounds simple, but you got to really wrap your brain around this. Isn't the easiest way to answer the question, where does the ant think he's going to step? Isn't the easiest way to answer that just to find out where he actually does step? Because he's going to step exactly where he thinks he's going to step, right? In that case. That's something that we'll come to call this very soon. We'll call this a limit that we can evaluate by direct evaluation or direct substitution, right? Because there are no tricks up our sleeve here. The function is exactly what it seems to be, right? It's a well-behaved function. It's continuous. Wherever the ant steps is where he thinks he's going to step. But the green function was not so well behaved. The green function is undefined at x equals 1, right? And so we had to take a different approach to this one, right? Because we can't plug in the value x equals 1 into g of x. That value doesn't exist, right? So what do we do instead? Okay, we used a calculator, good. We leveraged a little technology in this case. And what was our strategy? Okay, find out, yeah, we can kind of look at look at a table and we can anticipate based on the values where the ant, it looks like he's going to step, right? And this is what we saw. Agreed? And so what did we conclude the answer is? 3. Okay, does something about that bother you? Because it does me. I recoil at the idea of just using a numerical table like that to try to come up with an exact solution. Doesn't that seem a little hokey? I mean, how do you know that it's 3? It sure seems like it. And we could make some pretty powerful arguments that it has to be 3. Here's what we might be able to say. We could say, see if this makes sense to you. Because this is, I think it's important sometimes to just think out loud like a mathematician, and then you kind of get a sense of what that looks like, right? What that feels like. Would you agree that if I were to take this function and I were to zoom in more and more closely, what would I find? What's it going to do?
Get closer and closer.
Okay, what happens, let me ask you a different question. If aliens were to beam onto the surface of the Earth in a wheat field outside of Pendleton, and these aliens were alien kids, they didn't know anything about science, they might think that our Earth was perfectly flat, right? How come? Looks pretty flat, right? When you're that close to the surface of the Earth, it looks pretty flat. But then all the parents would have to do, these parent aliens would say, just beam them back up to the ship and say, well, look, that's where you were. That looks pretty spherical, doesn't it? Yeah, okay. What's the difference in those perspectives, though? They zoomed in, didn't they? Right? You zoom in very close to the surface and curvature gets eliminated. So once again, if I were to take like a microscope, and I were just to zoom in more and more closely on that spot, what's going to happen to that curvature? It's going to get very straight, isn't it? Right? Okay, if it gets straight and linear, what does that tell you about the values of x as you approach, as I get more and more, as I get closer and closer and closer to this thing, zoom in, it starts to look like a line. Shouldn't eventually the values on either side look linear, and it should start to look like you're proportionally far away from the exact answer with each step? Does that make sense what I'm saying? So let's look at this table of values again. If we get in very close, notice that we are almost exactly, well, we are, I mean, does that make sense? We're almost exactly the same distance away from 1 on both sides. If I make those steps really big, I shouldn't see that, because then it starts to become curvy and unpredictable. But at this scale, it starts to look pretty linear, right? And so there's one pretty powerful argument for us to say, okay, this is hokey, but yeah, but it works, right? Because when we zoom in, it starts to act like a line, and so we can do some stuff with that line that really does allow us to zero in on a more precise value, right? Let me just demonstrate what I just said. If I go back and I go set the table up, and instead of going by 0.01, what if I go by 1? Okay, that's not symmetrical at all, is it? See what I'm saying? Right? Okay. So as bad as it is, as much as it still bothers me, you sort of could lean on a numerical approach sometimes, you know, with some level of confidence, right? Another approach maybe we could take is we could use this technology and graphically we could just trace along. I'm not even going to do it, but would you agree if I were to do that, if I were to trace along on my calculator, I could sort of anticipate what that value is going to be? Bottom line, though, it's a pretty crappy approach. Wouldn't it be better to come up with something different? I mean, in a calculus class, you know, wouldn't ideally we like to be able to come up with an analytical way of doing this? When I say analytical, what does that mean? What do we normally, when we do analytical math, what do we normally get as an answer? Say it again? Formulas, maybe, yeah. If we're trying to find a value, usually we're going to end up solving an equation, right, and we're going to get an unambiguous exact answer. Well, we want to be able to do that at some point. We want to be able to use algebraic, abstract, mathematical methods and not do this hokey table thing, right? Come up with an exact answer. So that's where we're going to be going very shortly. Before we even do that, though, I want to take one more look at this stuff, just from kind of a conceptual perspective, right? Let me draw some pictures, and I want you to tell me some limits based on these pictures. Okay, so here's the x-axis, here's our function. Okay, yeah, we'll do this. Here's some x values. So what is, roughly, could you point to a place at least where this limit exists? Fill in the blank. The limit of f of x as x approaches a. Does that exist, and if so, whereabout is it? Okay. Here's my ant walking along the function. About there? Okay. So whatever value, I don't even know, I mean, I didn't put any numbers on this, but whatever that y value is, right, that's our answer. Okay. Let's just say hypothetically, it seems like it's about -1 if we're going by increments of, it's about -1, right? Agreed? Okay. What about up here? If I do the limit of f of x as x approaches c, as the ant or ants are walking towards x equals c from both directions, don't they anticipate stepping right there? Okay, well, what's the y value there? It looks like it's about +1. Fair enough? Questions? Does that make sense so far? Remember, the limit is where the ant thinks it's going to step, right? Okay. What about this one, though? Okay, undefined. How come? There's a break in the function, right? It doesn't work, does it? As the ant approaches x equals b from the left ant anticipates stepping right there, right? What about the ant approaching from the right? Well, this ant's walking backwards, and it anticipates stepping there. Those are different answers. Because they don't agree, this is no limit, right? Make sense? Okay. You with me? Okay. How about something like that? What do I call that kind of behavior on a function? See what it's doing? Exponential. It might be exponential. Might be some other kind of function. But both of them, what's this thing called?
No, we definitely learned this.
Yeah.
I know, I was trying to think of the word yesterday.
Asymptote. That's it. Good. Good. There you go. Okay. All right, so that's an asymptote. And so we would call this asymptotic behavior, right? Where the function approaches but never gets to the asymptote, right? Okay? So let's just say that this asymptote exists at x equals a. What's the limit here of f of x as x approaches a? Is there a point I can draw that the ant thinks he's approaching? So what are you supposed to answer is? No limit. Yeah. No limit. Later on, we can be a little more specific about this, but we're not going to quite do that yet. We can say some other meaningful things about that. Even though it doesn't exist, there's some interesting stuff going on there. But that's a place where the limit certainly does not exist. Okay? And then, I'll give you one more. So let's say the coordinates of that point are A1, and the coordinates of that point are A2 of that hole. What's the limit? Does it exist? Interesting question, huh? Does it exist? So in reality, in this bizarre two-dimensional world, if an ant steps on that point, he drops down there. He just beams down there for that one point. His next step carries him back up to the function if it's going left to right. That doesn't answer the question. I want you to tell me, what's the answer? What do I need to fill in the blank with? What's the value of the limit? What is it? It's 2. It's 2. How come?
Because it's stepping even.
Yeah, but he actually steps there. Is that a problem? No, doesn't matter. Remember, the limit, where he actually goes is completely irrelevant as far as the limit's concerned. It's where he thinks he's going to step is what the limit means, right? So the answer is unambiguously 2. Okay, so then, if we wanted to enumerate some places where limits don't exist? What's one kind of place? There's an example up there. What is that?
In the graph.
Say it again.
A break in the graph.
Okay, break in the function. Yeah. And we call that a large break in the function. Something like this. Right? By a large break, I mean it's not like there's just one point that's taken out. The functions approach different values from different sides, right? I just didn't want to write all that down, but you might want to put that in your notes. Right? The function approaches different values from opposite directions, right? What's another type? Whoops. Asymptotic behavior, right? Where there's infinite, the function has infinite behavior, right? That also can't work. There's another one, I gotta think of a function that this would apply to. This is gonna be kind of weird. Something like, what if we had f of x equals, probably the easiest one would be something like sine 1 over x. This is kind of an interesting function to think about. What's this function doing? What do we call when we have a function of a function? Freak out? Oh, now, come on. R's altitude, come on. What do we call that? Function of a function. Starts with a C. Composition? Composition of functions. Remember that stuff like f of g of x?
Yeah.
Okay. So this is a function of a function, right? It's a sine function of an inverse function, right? Now let's think about the behavior of this just for a second. The sine function, it doesn't care where it gets its input values. It's just getting input values, right? You're going to feed a function, you feed a function numbers, and it spits out results, right? What does a sine function by itself look like? So if I were to graph something like y equals sine x, what's that look like? Yeah, it's just a sinusoidal or oscillatory function, right? Something like this. Oh, that's there's a glitch. There's a glitch in the system. Right? Everybody agree? And if sine of 0 is 0, sine of 2 pi is 0, etc., right? Sine of pi is 0. Okay? So that's what a sine function looks like, where this is the x-axis. But we're not just feeding this sine values of x. We're feeding it the output of the inverse function, aren't we? Right? So how's that going to change things? That's going to be weird, isn't it? As x gets bigger and bigger and bigger, what's going to happen to 1 over x? It's going to get smaller and smaller and smaller, isn't it? Right? What happens as x approaches 0 is it gets smaller and smaller and smaller. What happens to 1 over x? It gets bigger and bigger and bigger, doesn't it? Right? So what's this thing going to do? That's going to make things very strange. It's going to take the envelope of this sine function and it's going to warp it massively, right? Yeah, what's it going to do? So we could say something here. Let's look at it. This would be a cool way to do it. I just thought of something. How about if we do this? What is the limit of 1 over x? And that's important because that's the argument of the sine function, meaning it's the function that's feeding values to the sine function, right? What's the limit of 1 over x as, this is new notation we won't talk about for a while, but just see if this makes sense, as x approaches infinity, if it gets really big. Yeah, what's that value going to approach? What's 1 over a really big number going to start to look like? 0, isn't it? That's going to look like 0. In fact, it would be that way if I approached negative infinity also, right? What's the sine of 0? Because that's what the sine function is going to see, isn't it? Sine of 0 is just 0, isn't it? Right? So would you agree that if I superimpose this graph on this, as we go clear out here, we're going to be approaching a value of 0 because the sine of 0 is 0, right? So clear out here at the tails, it's going to be pretty boring. It's just going to be asymptotic along the x-axis. If this isn't making total sense, do not panic. There's a lot of this stuff we won't talk about officially for quite a while. But what's the limit? You told me, another way I could write this, the limit of 1 over x as x approaches 0 is infinite, right? Agreed? It's infinitely big. So in here in the middle, as this ant approaches 0, what's going to happen? Well, 1 over x, when x equals 1, so somewhere out here at 1, this whole thing's going to equal 1. What's the sine of 1? I don't know, something going to be a little less than 1. So it's going to start to kind of do something like this, isn't it? It's going to go. And as it gets closer and closer to x, the pace at which this sine function is eating input values gets really frenetic. It just keeps increasing, right? So it starts to just go. How many times does it oscillate between there and 0? An infinite number of times, doesn't it? Right? Same thing from this direction. If we back up, it's going to do something. That probably should have been down there. Oh, you get the idea. It's going to do something like that. It's going to oscillate an infinite number of times. Well, where is it at 0? It doesn't exist, right? The function doesn't even exist at 0. So what's the limit here? Could an ant approach from the left or approach from the right and ever point to a single value where it anticipates stepping? No. Every tiny little step makes it move back and forth more and more wildly, right? Isn't that weird? That's very weird behavior, where you capture some infinite behavior inside a finite space like that. Interesting question. How much ink would it take for me to actually graph this thing accurately? Yeah, you couldn't do it. Couldn't do it. There's not enough ink in the universe. If every subatomic particle in the universe were ink, you still couldn't draw it. Right? That's weird. So does that function exist? Ooh, strange, huh? Yeah. So the answer to this is no limit, of course, right? So we're going to add this third category, and this is a weird category. You don't see this stuff very often. But we could call this oscillatory behavior, or oscillating behavior.
So does that also work with everything besides sine?
Oh yeah, it could work with cosine, it would work with, anything that's a cyclical function like that. You feed a cyclical function an argument that's going to get infinitely big, you're going to see the same kind of behavior. Okay. Make sense? Okay? All right, well, next step. And I'm going to skip the formal definition for now. We'll come back to that. It's really cool stuff, but it's pretty theoretical, and I don't want to derail our talk here. So what I want to look at next is I want to look at how we could just do a really simple example of how we could use a more solid approach to this, an analytical approach to finding a limit, right? We looked at some hokey numerical, and we could use a graphical approach, but how could we go back and deal with a problem like this guy, right? Without having to use such a hokey approach? Could we get an actual answer where we do some algebra, and we come up with an answer that says, okay, well, the limit is equal to that number, drop the 10, done with the story, right? It's non-ambiguous, okay? That make sense? I guess before we move on, any questions so far? How are we feeling about this? 5 meaning, I'm getting this, 1 meaning, what are you talking about? Just flash me a little, give me a little feedback here. How are we feeling about this stuff? Okay, all right. Okay, that's, yeah, the limit stuff, trust me, we're going to do this so much that you're going to have a really solid understanding of it and intuition about it soon, but I know this is all pretty new. This will help, though, what we're about to do. So let's go back and let's look at an example like, how about this one? What if we do f of x equals let's do that one. Okay, do we need to define a domain for that function? Are there any excluded values? 1. Okay, function does not exist at 1. So, okay, let's do two things. Let me find what is the limit of f of x as x approaches -1. Well, what's that going to give us? As I approach -1, I'm going to get 0, aren't I? And I can do that one by using direct evaluation, right? Because the function does exist at -1, and so to answer the question, where does the ant think he's going to step, we'll just find out where does he actually step, because that's where he thinks he's going to step, right? So if I evaluate this directly, I would get 0 on the top and -2 on the bottom, which is 0. End of story, right? That's where the ant thinks he's going to step, okay? How about this? What's the limit of f of x as x approaches 1? There's a problem, isn't there?
None.
What do I get?
None.
And I'll tell you what, we are going to get an answer. This is very similar to, in fact, I just should have done the same problem. I don't know why I didn't. It's very similar, though. We could have just done this problem, same thing, right? In fact, let's do that problem. Why not? Okay, let's just do that problem. We know we're going to get an answer, and we know the answer is going to be 3, right? But how are we going to, how much time we got? 5 minutes? Oh, good. All right, I got lots of time. Excellent. So let's make that cubed. And then if I made that cubed, isn't this going to be, that's going to change this answer. I'm going to get, what, 1? -2 over -2, is that right? Did I do that right? You guys double check me here. Right, -1 cubed is -1 minus 1. Right? Point is, we still get an answer, right? The ant, we know where the ant is going to step. But if I plug in 1, look what happens when I try to evaluate this directly. What do I get on the top? 0. What do I get on the bottom? 0. That's interesting, right? That is what we call, this is an indeterminate form, meaning we don't know. Jury's still out. It could be that it could be infinite. It could be that there is an exact answer that we just haven't found yet. But essentially, what this always amounts to for us in calculus is, oops, if I evaluate directly and I get 0 over 0, more work. We have to do something to resolve that indeterminacy. Okay? What can we do? Let's go back and look at this function again. So, So we're taking the limit of x cubed minus 1 over x minus 1 as x approaches 1. Okay, let's think about this from two different perspectives. And we probably won't finish this today, but I want to get you thinking about this intensely. Okay, one way we could think about this is purely algebraically. Why did this thing end up being 0 over 0? Right? Well, pretty simple, because both of those expressions have values of 0, right? Algebraically, is there anything I could do to either of those expressions to rewrite them in a different way?
Take the x, put the x cubed, and just x squared, and now take the 1
Okay, but I have to do something that's legal, right? I've got this expression here. Think about the options that are available to us. If I want to do algebra on this expression, the expression has to remain the same. So I could either add 0, which doesn't change it, right? Because 0 is the identity number for addition. Rarely do we ever do that. I could multiply by 1, which we do a lot, but in this case may not be helpful. Or I could take one of these expressions and change its form by either expanding it or factoring it or something like that. I can't take out an x, but I can factor that, can't I? Isn't that a difference of cubes? Right? So what's our pattern? This is good review. What's our pattern for a difference of cubes? Remember? Factoring pattern? Okay, we're going to get a linear and a quadratic factor, right? And here's how I remember this. So you know the linear one's got an a and a b, the quadratic one's got an a squared and an a times b and a b squared. And whatever this operation is, it goes there. We get the opposite there, and this one is always positive. Okay? Make sense? So then, oops, down here. So what does this top expression become then in factored form? X squared. Good. Everybody see that? Okay. Divided by x minus 1. Okay. So that we could rewrite f of x that way if we want to. Right? Okay. Anything we can do here algebraically? Okay. We could cancel factors algebraically, right? Okay. Now, but we got to be careful with this. If I do that, I've changed the function a little bit, right? I can do that. And it makes sense, doesn't it? Because in my limit, as x approaches 1, let's look at the values that each of these factors approaches. As x approaches 1, that factor is going to approach 0. That factor approaches 0. But this factor does not approach 0, right? So by algebraically canceling those factors, you see that strategically that makes sense because I'm eliminating the indeterminacy, right? Meaning the 0 over 0 behavior. We get the 0 on top and the bottom from the behavior of that factor that we're canceling. Do we see that? Okay. But if we do that, we have fundamentally changed the limit. Now we're taking the limit of a different function. We're taking the limit of x squared plus x plus 1. Let's look at something on our graphing calculators here real quick. So let's graph. Okay, I've already got this one in there, right? We looked at this graph yesterday. There's the graph. Okay. Let me also graph. I'll jump down here to y2, and I'm going to graph x squared plus x plus 1. Looks the same, doesn't it? Is it the same? the same.
Same without.
Oh. Okay, so let me turn one of these off. I'm going to turn the bottom one off. Go back and graph. Let me remind you about something. If I evaluate the function at 1, I get nothing back. It doesn't exist there. Aha. Okay, but look what happens here. If I turn the top one off, turn the bottom one back on, and if I evaluate this function at 1, what am I going to get? 3. What do you know? Great trick. So what did we do there? That was an awesome trick we just did. We just pulled. What we did was we traded this original function f of x for a new function. Let's call it g of x. G of x equals x squared plus x plus 1. And this is a little bit of a cumbersome way of saying it, but this is the way we mathematicians say this. We traded f of x for a different function that agrees with f of x at all but one point. Essentially, we filled in the hole, didn't we? Right? We created a function with the same envelope, but filling in that hole. What's the advantage of that when we're trying to find a limit? Yeah, now on this yellow function, the ant is going to step where he thinks he's going to step, right? So this gets a little confusing, but by graphing this yellow function, which is this guy with the hole filled in, right? We have answered the question, where does the ant think he's going to step on the green function? By answering the question, where does the ant actually step on the yellow function? Because they're the same thing. Agreed? Okay? And so in terms of just doing the math, just doing the algebra, now the answer is pretty easy. Now we can evaluate this by direct substitution, right? If I plug in 1, what do I get? 1 plus 1 plus 1 equals 3. Make sense? Okay? You try one. We have time? Yeah, we have time. Okay, so here's the function. Let's see, how about... Okay, I want you to take the limit of f of x as x approaches -3. Ideas. What'd you do? Okay, what's the top factor into?
X plus 2.
X. Okay. So agreed, we're going to get 0 over 0 here, aren't we? Right? And you always got to try that. I mean, what if I had asked this question where x approaches 5. Would have worked, right? We could have just applied direct evaluation right from the start, and it would have been fine. The problem here is that we get 0 over 0, right? We can though, can't we? We can cancel, algebraically, we could cancel those factors. And so then this is equal to the limit of x minus 5 as x approaches negative 3. And that is amenable to direct evaluation. What do we get? That's it. So what are the coordinates then of the point that the ant anticipates stepping on?
3.
Yeah, negative 3, negative 8 is where he thinks he's going to step, right? Okay. What happens when he gets there? Goes away, I guess, right? So what do we do? Let's just summarize this. What have we really accomplished here? So we identified what the meaning of a limit is, and we'll go into much more detail with that. And we've established some techniques for evaluating a limit, coming up with an answer for a limit, right? Taking the limit, we'd say a lot of times in calculus, so take the limit. Either we can do it in a hokey way, graphically or with tables, or we're starting to develop a little bit of a strategy here, and this is just the tip of the iceberg. We're starting to develop some approaches to analytically getting an answer. And we get that by canceling what I like to call the offending factors. We're going to cancel the factors that cause this thing to have that indeterminacy, right? The factors that have zeros at the value we're approaching, right? Okay, I'm going to put up a couple of assignments, won't we do tomorrow, but I'll put up a couple of assignments on Math Excel that you can kind of start to work through, okay? And we'll take a little bit more of a look at this tomorrow. I'll take some questions, so if you get a chance, you know, maybe work through and do a couple problems from the assignments just so you can get some questions answered tomorrow, okay? Yes? Say it again. Oh, yeah, if you're gone, just, I mean, you may not be able to do the whole thing, but I won't make them do, is everybody going to be here on Tuesday? Everybody going to be here Tuesday? So I'll make them do, how about I'll make them do Wednesday? Or at least the first one do Wednesday so you can get questions answered even if you're gone tomorrow. Okay? All right.